Our first speaker is Nicolae Tusinschi from OneSpin, and he will be giving his presentation now, a methodology to verify functionality, security, and trust for RISC-V cores. Nicolae, the stage is yours. Thank you very much.
Thank you, Alex. So, hello, good morning, everyone. And I'm pleased to be the guy that presents this joint paper on a methodology to verify functionality, security, and trust for RISC-V cores. And 2 words about me. So I think we're getting some background noise. Okay. Where I was. So yeah, my name is Nicolae Tusinschi. So I'm with OneSpin. I'm the product specialist for design verification, and in my working time, I'm doing a lot of stuff that is related to developing verification solutions that are having the formal technology under the hood. But yeah, so pleased to be here, pleased to talk to you, and I'm in this 25 minutes, I will try to give you a bite of what we are doing for processor verification. And namely, what we target now is the RISC-V ISA implementations. And yeah, so this is the outline. I will be talking about a bit of RISC-V and what is behind it. Then I will dive into what are the processor verification challenges and how formal verification can help in this regard. Then I will introduce the heavy lifter that we have developed, the processor integrity verification solutions. It's a semi-automated solution to formally verify processor implementations. Some words, I don't know how much I can get to present under the hood. It's just a brief idea on how this works under the hood. For those that are interested, feel free to ask a question at the end of the session or to get in contact with me. Then results, of course, how we got results. So we have prepared two results that are actually public and some conclusions on maybe some future work and so on. Okay, so pleased to be here. Let's start. Yeah, before we start at OneSpin, we, on top of the processor integrity solutions, we are developing the verification apps solutions to make sure that IC integrity verification is achieved. We target most of these phases in the verification flow, design, integration, implementation, and we focus on areas like functional correctness. Actually, this is my area of expertise, and then we have the safety area and the trust and security. In this paper, we talk about the functional correctness, so making sure that the RTL is doing what the spec is saying, and also on the trust side is we make sure that we are getting a full, complete spec. All right, so let's start. RISC-V, I think everyone is aware of the hype that is around it. So it started actually 10 years ago at Berkeley. So the beauty of it is that it's an open source instruction set architecture with a wide range support for a variety of applications. It's structured in a way that allows many possible configurations, and the space that is allocated for custom extensions is also has an increased, there is a lot of space left for customs extensions. I think there is every day we get some notifications on new members joining the RISC-V community, and actually the ecosystem is maturing quickly. So there is also toolchain simulators, verification, and other pieces that are making the ecosystem, and there are also non-profit commercial grade cores that are like the Open Hardware Group, who is working in this area heavily. All right, the RISC-V ISA, it's an instruction set architecture that is split modularized, I would say, in extensions. So basically, there is plenty of extensions for I, M, A, F, D, C, E, etc. So basically, the mandatory one is the integer. So there is no implementation without having this extension. And then on top of that, engineers can build more functionality for the course, like adding some multiplication and division, the M extension, the atomics, the A extensions for atomic read, modify, write of memory accesses, floating point, single and double precision, compressed, and bit and some other extensions that are being there. Beside the extensions, it's 32 registers that can be 32, 64, 128. The embedded version is halves the registers by having only 16. The free privilege levels are there, plenty of CSRs, and also the spec is, there is a spec, nice spec for interrupts and exceptions. So this is the instruction set architecture. It's structured in 3 specification papers, which are taken into account when we develop the processor integrity. All right, so on top of the RTL, so there we have the verification challenges that for the RTL itself, for implementation, checking that the core is compliant with ISA. Of course, it's a significant task, but it's not enough because it's there is a component of the microarchitecture, and we ensure that the functional correctness is achieved for that part as well. And this is very core dependent, so and it becomes a very complex task as well. Usually, the designer, the architect of the core has the freedom to select the desired configurations, and usually the pipeline implementation is optimized for power, performance, area, etc. And when you have such cases, usually the corner cases are something that are there, so it's impossible to foresee, and mostly these corner cases are hiding in the control part, especially in interrupts, in exceptions, privilege modes, and there is a reason why people have some awareness of this is the place where formal verification is a good target to apply. And on top of that, we have the risk of someone exploiting the side channels, and this is where the security vulnerabilities and hardware trojans are also an RTL verification challenge. Okay, I believe someone forgot to mute the mic. So yeah, formal verification is great. So it's great in finding these corner case bugs in the implementation. It's the only technology that can provide exhaustive verification by its and the proof of bug absence. And but formal verification would say requires some expertise to write good quality assertions, and it's difficult to assess the quality of these assertions. So we will see how the solution, the processor integrity solution, is targeting actually this aspect of the quality and the gap of the assertions. Another challenge of the formal is the complexity issues. So the inconclusive proofs are a common challenge that also needs to be tackled. What we propose with the processor integrity solutions, so it's a verification methodology that is taking some inputs and is generating some outputs, and as an input to this methodology we have obviously the the core RTL, so the implementation itself, which is the input to the tool, and then we are having the spec, the RISC-V instruction set architecture specification, and on top of that there is the missing part, which is very core dependent, and it's actually the design implementation decisions. So this is where the number of pipelines, the timing is specified, etc. What you get after doing the RISC-V verification methodology is you end up with a trusted RTL because the assertions are proven to hold exhaustively. So you're getting a trusted RTL. And because we have a way to make sure that the test bench that has been developed makes an executable spec, so the RTL is equivalent to the spec. Another outcome is you are getting the trusted executable specification. So these are the two main advantages that you are getting applying this RISC-V verification methodology that is incorporated in the processor integrity solution. All right, so the processor integrity solution itself, as I pointed out, is taking the input, the RTL, and the first step that is performed is actually does a design analysis and extracts information on the design info. It can extract information on the architecture, so the extensions, the configuration. Then it has the capability to extract several parameters, register maps, mapping, user extensions, pipeline depths, IOS mapping, etc. Once this information is extracted, so we are here on this step. So this information is actually then provided to the solution, to the RISC-V modeling layer. This information is used to map to the architecture. Under the hood, the specification model, the standard specification RISC-V ISA model is there, and together with the information from the information extracted from the design, there is assertions are being generated, and these assertions together with the RTL are ending up in being verified by the formal verification engine, which is optimized for these processors, and you are getting the trusted RTL. Yeah, so as I pointed out, it's optimized for exhaustive unbounded proofs, and it proves that you're getting a proof that SVAs achieve 100% coverage, so no gaps. Of course, when you're getting failures, you're getting the capability to debug the failures, and usually it's a nicely way to debug where the source of your packet is. All right, so how the assertion that is generated under the hood, so it uses the so-called concept of operational assertions that we have in OneSpin, and this is making use of the SVA. It's an SVA use library of operational assertions. So basically, you are having a trigger part, and then I will explain what the start state means here, which are the inputs, and then you are having an operation, and what you are trying to capture is actually the effect of these triggers and operation over the time. So you see here we have a start state and end state. So in case of the operational assertions, we prove that so when an instruction, an exception is triggered to be executed, then the core starts in a state. And these states can be the register file, the program counter, the CSRs. And after this instruction or exception is being applied, the current state of the core is actually updated, and we need to make sure that the updated is done accordingly to the spec, the ISA spec, and also the core specific core implementation spec. So yeah, it captures the effect of instruction exception on the architectural on the architectural state, and actually it's decoupled from microarchitecture details. So there is a line which decouples the ISA spec and the microarchitecture details. How we make sure that we are not getting that we are not missing any functionality. So we have the capability to make sure that what we have in terms of assertion is forming an equivalent spec of the RTL. For that reason, of course, we are ending up having from specification a verification plan, and then we end up having these semi-generated assertions that are run into the property checker. So if they are failing, you would need to debug the core and fix it. If these are not failing, then you're getting an exhaustive proof that, for example, this server test bench you developed holds. But in order to make sure that the test bench is complete and you're not having any gaps, you would need to run the completeness checker, which is an additional check on top of the properties that are being developed. And this completeness checker, in case it fails, it might point out to a specification issue or a verification plan issue or an assertion issue. So if you're having a functionality that is not in the verification plan, then you are ending up with the completeness checker to fail. The same happens for specification, and of course, if you are having some issues in your operational assertions and they don't form a complete spec, this will be reported. So in other words, on how to think about this completeness checker is taking a puzzle. So you're having like a puzzle to build. Each assertion is a piece in your puzzle, and then you would like to take all the pieces and put them together. And if there is a piece missing, then you will get it. You will get this information from the completeness checker, or if there is a piece is broken, also is reported by the completeness checker. So what do you get out of it? So we get that the proof that ISA's executable model and RTL are equivalent. So for any input trace, the two models produce the same output, and any undocumented or deliberated hidden function is detected. The results, this is the interesting part. So first in line is the RISC-V core. Now it's created by the open hardware group. It's the CV32E40P. It's a 4 stages, 32-bit. The target is commercial grade quality, and we applied the solution to this core. So not to mention that we decoupled the core, so the processor integrity targets the core, so there is no interest to apply. I mean, there is interest to apply, but there is no, the caches, the instruction cache, and are outside of the processor so integrity solution. So we focus on the core. Of course, we can verify the other parts as well. And the results that we found on the RISC-V core, it's actually a decent amount of failures for exceptions. As you can see here, we have like 1, 2, 3, 4, 5, 6, 7, 8, more than 10, and are related to the exceptions. And this is proof that in most cases the bugs are residing in this area, which is, I would say, nearly impossible to exercise with a simulation approach. The other guy that we have applied the solution is the Rocket core. This is a 64-bit implementation compared to the RISC-V. And yeah, it's generated from Chisel, so it's actually not very readable. And it's mostly in order. There is long latency instruction division that completes out of order. And yeah, when we applied the solution to the Rocket core, there is also exception errors. This is one specific bug that is related to the security stuff. So there was an undocumented non-standard instruction that had the opcode, and actually later on this was appeared to be the sys instruction, and some other issues that, for example, the div results after the div instruction has been completed 30+ cycles, the result was not written back to the register file, and this was overlooked by the designers. Alrighty, so I think I have like perfect timing, so 2 minutes to conclude the stuff, and then we can get into the questions. So functional verification of the processors is challenging, and many configurations, many cores, complex implementations. Formal verification using automated solutions, so we prove that the core complies with the ISA, detect all corner case bugs, including custom extensions, identify security weaknesses, vulnerabilities, and hardware trojans, and it's applicable during the course RTL development and IP integration. So while you develop, you still can apply the solution on an iterative way. On this note, I would like to thank you everyone who attended the session, and if you have any questions, just feel free to ask.
Thank you, Nicolae. Are there any questions from the auditorium? Okay, there is a question in the chat. Can you elaborate a bit more on the real-world bugs?
Real-world bugs on which core, in which context?
You found in Rocket Core. Okay, so that's what the person is. So the person asks to go back to slide 15.
I think this one is the guy with the Rocket Core.
17, exactly.
Yeah. So on the Rocket Core, we applied the solution, and first going through the bugs. So the division itself was controlled by a scoreboard, and because it has out of order completion, when the completion was actually the instruction was retired, the result is supposed to be written back to the register file when there is a free slot, but in fact the wrong result was written to that register file. Instead of having the result from division, the result from another instruction was written to that specific location. There is, because the Open Rocket doesn't have a stalling, so it has the replay mechanism. There is plenty of illegal opcode instructions that are not triggering an exception, but actually are being replayed. And the most important one was, I would say, that is related to the security stuff. There was an instruction that was not documented. So basically, the checks were failing because there is an opcode, and this opcode does not trigger any exception. And there is no specification what this instruction was supposed to do. And the most interesting part is, okay, the designers specified that this is a non-standard instruction, but there was they forgot to set the user extension in the MISA register of the implementation. And some other access to non-existing, where I was 17. Access to non-existing CSRs, didn't raise illegal instruction exception, it's still open. And then there is for DRET instruction outside of debug mode, and DRET instruction tied to MO status. So there is all the bugs are logged in the GitHub with a better description, a complete description, so you can give a look at the issues that are there.
Okay. Thank you very much. There is one more question from Guido Ferrari in the chat. Which property language description has been used for develop the verification assertion for the core? SVA, ITL, or title? Are there some advantages on using one of the mentioned above compared to others?
So the operational assertion concept is using title, which is a library developed from SVA. So it's part of the OneSpin solution, the processor integrity solution. So it's in title. And the title has the advantage that it can capture best the timing diagrams and having the pipeline implementation that is fitting into this description is title in which it's implemented. Of course, there are a couple of constraints on the interface that are written in SVA, but it's the other side. So it's title.
Okay, cool. Thanks. I think that answers the question. We have time for more questions, I think. So there's a question from Lukas Jünger. Have you analyzed other open source RTL as well?
Yes, we have the Rocket core configuration and also the IBEX, which is a derivative from it's a zero risky, so it's more or less, but it's instead of a 4 stage, it's a 2-stage. It's a bit more simple, but in terms of the pipeline and stuff like this, but I wouldn't say that it's simpler than risky because it has all different timing and so on. So the IBEX, the zero risky, and the Rocket are the guys that from open source that we applied it to.
Okay. Thank you. Nicolae, do you plan to hang out in the 3D world also later if people have more questions for you?
Sure, yes.
Okay, cool. So meet Nicolae later. We are approaching the full hour, so and there are also no more questions on the chat.